think it's about 3 minutes past 9, so I think we can start on our first webinar series on Leaky Deltas. This is in anticipation of the Leaky Delta OCB workshop we're planning for next year. So what we'd really like to start off with is take this Menti poll that we have a link to in the chat. If you have a chance, please look at the chat. There should be a link. And we'd really love to get your feedback on the questionnaire we have there. And while we wait for people to respond, I'll just start off with our idea about why we're planning this workshop, what is our goal, and what we want to get out of this. So this would be a scoping workshop like the ones we have done in the past through OCB, and it will be held in February and March of 2025 in Baton Rouge, Louisiana, right on the Mississippi Delta. And the aim of this workshop is really to synthesize our current understanding and knowledge gap of the role of Delta in global carbon budget. It's a comprehensive plan to look at the sources, sink, and transformation of carbon along the Delta Ocean continuum. So we'll start off from the Delta habitat, mangrove, salt marshes, to Delta leading front, all the way to the shelf. So the entire transit of the Delta carbon cycle. So with that, we are going to just take a pause and hope to see some feedback from the Menti poll before we jump into the other aspect of our presentation. So I'm going to hand over to Liz.
Yeah, thanks. Okay, let's see if I can pull this up successfully. I am not able to get Zoom to come up right now and give me options. Can you still hear me?
Yes, we can hear you.
Yes, we hear you.
Okay, I got Zoom back. Bear with me a minute.
Here we go.
Okay. How's it look?
Perfect.
Okay, great. All right, so here's what we have as our initial things. We have a lot of sediment, a lot of nutrients, and river. And it looks like the results are still coming in. And I think it's stabilized for now. We have some specific rivers as well, some other processes like subsidence, sources of carbon dioxide, loss, coasts, lots of interesting processes. And hopefully we'll get around to exploring some of these as well in our seminar series and in the workshop. So let's move on to, we have another poll for the audience. We'd like to know what you work on. So please let us know. And if it's something different here that you want to share, you can drop it in the chat too. Okay. So we have a lot of people working on both. So really nice, some good interdisciplinary contributions and participants. And nobody here works on neither. So I think then this is a great workshop for you. Should we give it another minute or move on? What do y'all think? Let's go to the next one. I think we've got good answers here. So if you could drag a pin and show us where you work, whether it's a certain landscape or region that you're working in, or maybe it's your laboratory.
Yangui, your hand is raised. Do you have a question?
Oh, I'm sorry. I pressed the wrong button. I
Oh,
have no
that's okay.
I'm sorry. I just yeah, sorry. Yeah, I just made a mistake.
Okay.
Uh,
Hey, pretty wide distribution of places as well. Very cool. Quite a few in Europe. Europe's small though, so it's hard to get real specific on this map where you work in that region. And some North America, South America, some in Southeast Asia.
You don't allow more than one place to be submitted.
Oh, no, really? I think then that's something I need to get more familiar with Mentimeter to do. Are there other places you'd like to share with us that you work?
You can
If
put them
there's
in the
other-
chat.
Yeah,
Put them in the
drop them
chat too.
chat too. Ah, we have Rhine, Gulf of Papua popping up in the chat. All right, well, let's leave this up for now. If you want to add more places, it's still open. And I'm going to stop sharing and hand it back to Kanchan. And he'll explain more now about our webinar series and workshop.
Thanks, Liz.
Yep.
So jumping right back on what this webinar is about. So what our goal is to meet every 2 months, once in every 2 months, and have 2 talks in each of these sessions. And we continue to do so till our workshop next year. And this, we hope, will allow us to kind of get a community going for all the different aspects we want to kind of touch in the workshop. And here are some of the tentative sessions that we have planned as a part of this proposed workshop. We can see it has the whole wide swath of deltas: ocean biogeochemistry for the shelf area, ecosystem for the delta land surface, salt marshes, mangroves, seagrass. And also we're interested in novel methods because we know these areas are very transient. We need to have longer term capability in terms of observation, connectivity for hydrological connectivity and their impact, perturbation like extreme events, drought, storms, and of course, to integrate it all, we need a modeling approach. And then I'm sure there will be other topics that we haven't yet come up with. And that's where we would like to have the community involved through these talks and these webinars to come up with other topics. We still have enough time on our workshop to have at least 1 or 2 community-driven topics that we can include. And that's kind of our goal, is to have these webinars where we'll touch on each of these topics by inviting speakers to come in and give presentation. If you're interested in giving a talk in any of these areas or any other research areas, please shoot us an email and I can just leave the organizer names up here. So we have a list of organizers here. They're all listed on the website. at the bottom. So if you just search Leaky Delta OCB, it should take you right to that website, and all the people who are involved with organizing this workshop is there, and feel free to email any of us, and we'll be happy to respond back with any queries you have. And I think and that's all I have before we start off on our talk for today. But one more important thing I wanted to kind of point out is, in addition to all these webinars, we're planning to have sessions that are kind of geared towards Delta focus. And here's one coming up in the 2024 Goldsmith session on biogeochemical cycling in river deltas. We will plan to have some other sessions at other conferences, but for now, this is the one that I wanted to point out if you guys are interested. And with that, I will again turn over to Lise.
Are we doing the poll for dates now? Okay. Okay, so we have a poll for dates as well, and we're curious to know what dates in 2025 best suit your schedule. So I'll advance to the next slide. I'm not going to share my screen for this because we don't probably need to see it, but now it's available to vote on either February 10th through 14th, 2025, February 17th through 21st, 2025, or March 17th through 21st, 2025 in the Mentimeter. Is that accessible to everybody? Can you give me a thumbs up if you're able to see it now? Yep, okay, I see some answers are coming in. Okay, thank you. That's really helpful for us as we organize it to know what dates people prefer. So please feel welcome to respond to that. Okay. And I think back to you, Kanchan, yeah?
Thanks, Liz.
Yeah.
So what we're going to do now, so please respond to that poll about what date most of the folks actually prefer. We have tried to schedule it to avoid Mardi Gras. It's going to be in Baton Rouge, Louisiana, so we have to make sure that we avoid the traffic. Hopefully that will allow the flight tickets to be cheaper and easier accommodations. So I will really love to get your feedback before we set the final date. So with that, I will start this introductory webinar off by having our first guest speaker of the series. It's my pleasure to have Dr. Christophe Rabouille to give the talk today. And what I would like to, I think many of us know him. He has been in the Delta biogeochemistry and Delta diagenesis work for a long time, really not a number of nice papers that many of us have read. So I would start by saying that Christophe is currently involved in this big scale multi-institutional project, which is huge in impact in terms of understanding deltas. And I think it's titled The Observation and Anticipation of the Evolution of River-Dominated Ocean Margins in the 21st Century. And I'm sure he'll be talking a little bit about it. But before we jump off and I give the mic to Christophe, I'd like to introduce him. He is a researcher and director at the LSCE since 1991, and he has a varied interest from aquatic biogeochemistry to sediment early diagenesis, ocean acidification, carbon cycle at land-ocean interface, hypoxia, and also anthropogenic and climate impact. With that, Christophe, it's a pleasure to have you to give our first talk. Thank you. I'm going to hand it over to you and stop my share.
Okay. Okay, thank you, Kanchan. Can you hear me well? Yeah?
Yes.
All right. Then I'm starting my talk. First, I would like to thank the organizers of the OCB Leaky Delta webinar series for inviting me to give this first talk. It was quite a short notice kind of invitation, but I think that was a good idea to start with that. So I'd like to talk today about the biogeochemical dynamics in deltaic sediments, and I will raise two big factors that I think are important in constraining the biogeochemical dynamics in these environments, which is the organic matter origin and the event-driven variability. Of course, as you all know, this work well, our work has been a long-lasting work for the last 20 years, and it's been made with a lot of collaboration with a lot of students, postdocs, and colleagues here at LSE. And also we have this long-term collaboration with Georgia Tech also, which I hope at some point we'll be able to show also some of the results we had together in some other deltas. Well, I will start with a very rapid introduction. I'm sure a lot of people in the coming webinars will also do very nice introductions. And the time is quite short for presenting what I want to present. But I will go on make an introduction on rheomars and carbon. What is the relation between the two of them? First, I'd like to really acknowledge the fact that the deltas and estuaries also not only the interface between the river and coastal seas, as is very often proposed, but is the real interface between the land and the ocean. So it's really where the land eroded and transported to the rivers meets the ocean through the coastal ocean, but it's very often that these rivers through the deltas, they export material to the open ocean, and this something that we should keep in mind. So it's really one of the most intense interface between the land and the ocean, not only the rivers and the coastal seas. Okay, well, they represent a very small amount of the world ocean. It's only 0.3%, as Wei Junkai pointed out in one of his annual review paper. But they are really hotspots of burial. We all know that. They bury almost half of the total organic carbon in the ocean, and it's especially true for terrestrial organic carbon. Terrestrial organic carbon is 80% of this carbon is buried in delta sediment. Okay, so burial deltas are main hotspots for burial, but they're also a hotspot for biogeochemical reactions because they reprocess or they expel an outgoing CO2 flux of 0.2 to 0.5 gigaton per year. So it's also a hotspot for CO2 fluxes, and you can see that somewhere here in one of the drawings that Wei Jun did some years ago, where you can see that estuaries are a source of CO2, which is almost equivalent to the sink of the continental shelves. While these numbers are still discussed in the community, but it's amazing to see that with such a small amount of the surface of the ocean, it represents such a large source of CO2 to the atmosphere. Also, I'd like to acknowledge some of the Brent Mackey and Mike Dagg effort in 2004. Some of you were probably not in the community at this time, but they introduced the term of rheomar, which was published in this report, and which has been one of my main words for my career. So I'd like to acknowledge that, and I will talk about it later, which this rheomar stands for the river-dominated ocean margins. Okay, when I received the invitation from Kanchan, I was thinking of 5 main topics that I could go through, talking about these rheomars and their interest in the biogeochemical cycling of the ocean. They are listed here: the carbon recycling, the extreme events, of course, but also the carbon burials, the rheomar on CO2, the alkalinity source that sediment can represent, or also the hypoxia in the bottom waters. So For today, I will only restrict to two of these terms, which is the carbon recycling and the origin of mineralized organic carbon, and the extreme events, because I think the time is pretty short. But there will be occasion that that some other people from a group or from some other group will talk about the other aspects that are, I think, prominent for the deltas. So our study area is the Rhone Delta. The Rhone is a medium-sized river. It ends up in the, you see that there is a map of France here, which is in the in Western Europe. The Med Sea is in the south. And so the square here is the one that is enlarged in this picture. This is the Rhone River. And the Rhone River is a medium-sized river, I was saying, has 5 to 10 million tons of sediment delivered each year. But it's really a highly viable river with event-driven deposition most of the time. I will come back to that, of course, later. And this river, you will see that in the rest of my talk, is split into 3 different zones. The proximal zone, which is with the near river zone, we call it the river mouth very often. The characteristics are large sedimentation rate, up to 30 centimeters per year. So it's with the sediments are really piling up very quickly, and it has a large mineralization rate. You will see that afterwards. There's then the prodelta here, which is the cone of deposition of the material issued by the river, delivered by the river. The characteristic is also a large mineralization, but it has a lower sedimentation rate, like by 5 centimeters per year, something like that. It's still been investigated because the numbers are hard to collect with that high sedimentation rates. And then the distal shelf, so which is also fed somehow by the river, but not only. It has a lower mineralization and a low sedimentation rate by 1 millimeter per year also. So what we use to study this delta, we use several the tools of the trade. We use in situ profiling for oxygen and pH. You can see that on the left. Coring on pore water extraction. Some of you are familiar with it. We use rhizons to extract the pore waters. We do a bench of analysis. Here I put some of these, the DIC and alkalinity, of course, on sulfate, which is prominent over there. But we use also a lot of different other methods for measuring phosphate, ammonium, nitrate, yes, iron, manganese, and so on. And in that talk, I will also emphasize the radiocarbon analysis we do on the DIC. So for this, we use extraction of the CO2 on these lines, and an AMS to measure the C14 that is extracted from the DIC. We also use early diagenetic modeling. We recently published with Stanley Moore in 2022 a new model that is based on the reaction transfer model, which is non-steady state and is linked to a flood deposition module, which I think is really relevant for deltas. Basically, it encapsulates all the reactions of early diagenesis. It has a viable flux. And it has a module that is capable of placing a new layer of sediment at the top of the sediment and calculate over time how much of the changes in both the solid phase and the distal phase evolves over time as calculated by the model, which contains all the processes, diffusion, advection, and a biogeochemical cycle for the elements that we generally look at. So if you want more information about that, you can go to this paper, which was published in GMD. Okay, then I'll go to my first part, which deals with the recycling of organic matter, its intensity in that delta, and the origin of mineralized OM. How do we cope with that? First, I want to show some very quickly how carbon recycling intensity can be traced by the oxygen in situ microprofiles. Here again, the map with the Rhone River here, again, the proximal, pro-delta and distal zones. And you can see right away from these oxygen microprofiles, here is the oxygen, here is depth in millimeter, how the oxygen profiles changes from the very near region, the proximal region, where the penetration depth of oxygen is only 1 millimeter, to the more distal region, where the penetration depth of oxygen is around like 8 to 10 millimeters. So this is a large change in penetration, which stresses the intensity of organic matter recycling between the two regions. So I will just tell you quickly that we can calculate the diffusive oxygen uptake from these profiles, taking the gradient at the sediment water interface and multiplying by the porosity and the diffusion coefficient. You will see that I will come back to that point later. And these are results that were published already 10 years ago or more in several papers that you probably have read. Also, during the talk, I will emphasize this gradient from the river mouth to the shelf, and you will see several times that the distances from the river mouth will be calculated along that transect. So if we go to more deeper in the cores, like going to the dissolving organic carbon, for example, distributions, you see that there is a large variation from the proximal domain to the distal domain. Please look at the scale here, which goes up to 50 millimoles per liter in the proximal domain and only 5 to 6 in the distal domain. So it gives you a feel that with this variation by factor of 10 in DIC concentration at depth, that there's a large difference in the intensity of the organic carbon being mineralized and producing this DIC in the pore waters between the river mouth, so the proximal zone, to the distal region. If you look at the bottom here, the sulfate profiles, you see right away that in the proximal zone, the sulfate depletion is almost complete. In most instances, around 40 to 50 centimeter. And this traces this sulfate reduction, which is the main digenetic pathway. You can see the equation there. And if you plot the delta DIC, so the variation of DIC versus the delta sulfate in the proximal sediments, then you'll find a slope that is almost 2. So that means that you have the stoichiometry of the sulfate reduction. So sulfate reduction in the proximal zone is the prominent digenetic pathway. If we look at benthic fluxes, so the diffusive oxygen uptake, the diffusive oxygen uptake on the left, you see that it decreases very fast from the river mouth, which is located here, to the shelf, and then flattens out on the shelf to levels that are around like 5 millimole per square meter per day. And you see the same kind of pattern here from the proximal zone here for the DIC fluxes that are around 60 in the 50 to 60 in the proximal zone here, and decreasing in the pro-delta and the distal zone. So we have a large biogeochemical reactor near the river mouth, and it shows a significant decrease offshore, which is due to this point source from the river, and that gets diluted on the shelf. Now I come to the point of how to get to the origin of mineralized organic carbon. So I told you before that the delta is fed by river floods, and these river floods, they deliver large quantities of organic matter, but they have very different kind of degradabilities. So the lability of the carbon is very often quite low. The organic carbon can be linked to soil matrices, for example, or also it can be lignin organic matter, and this has a poor metabolizable quality. So because we see that the organic carbon mineralization is very large near the river mouth, we might ask ourselves, are there other sources available for mineralization? And if so, can we trace their origin? So first, the starting point of this is that there is only a minimal share of the organic carbon deposited, which is mineralized. We estimated that some times ago to 10%, with 90% being preserved. So most of it is buried and not mineralized. So a minor fraction only of this deposit can play a major role in mineralization. So it's interesting to investigate what part of the organic matter is mineralized in these sediments. So for this, we use the paired isotope technique, which uses C13 and C14 of the pore water DIC. So again, here you see for these stations in the proximal zone, the increase of DIC up to, in this case, 40 millimole per liter. You can see that here. Whereas if you go closer, if you stay further away on the shelf, you see that the increase is very limited. And if you look at the composition, the isotopic composition of DIC, I will start from the right panel here, which is the delta C13. You see on these black dots, for example, that the signature of the DIC in the pore waters very quickly reaches values around -25 and can go down for other stations in the pro delta down to -30. So if you know a little bit about the delta C13, I will remind you of the terrestrial signature of the C13. If we go to C14 now, you see in these black dots that it reaches values around 400 to 500. And for those of you who are familiar with that, they know that most of the time the delta C14 of the organic matter or of the DIC is negative. And I'll come back to that point right in my next transparency. So from this profile, we can estimate the signature of the mineralization, the organic matter, which is mineralized, and that gives this signature to the pore waters by doing these plots that were inspired by Bob Haller, where we plot the signature times the concentration of DIC here versus DIC, and the slope here is the signature of the mineralized organic matter, the organic matter that feeds this DIC pool in the pore waters. And here you see -27, which is very close to the organic matter, the terrestrial organic matter in that region. And when you do the same kind of thing for the C14, you find a signature of +409 in that case, and which is very positive. And this positive signature tells you something about the origin that I'll go back also in my next transparency. So you can do that with different stations that we have. So those in the proximal zone, this one in the pro delta, and this one in the distal zone, and you end up with at least for the proximal and pro delta ones with the values of delta C13, which are really close to the terrestrial organic matter, -27 to -25, sorry, and the very positive delta C14 overall in that segment. The very large delta C14 points towards an addition of delta C14 to the environment, and so we think and we believe that it's linked to the nuclear power plant that are allowed to discharge some of the C14 in DIC in the rivers. Of course, all this is controlled and legal, and that enriches the river water that feeds the plankton. I will, before I go into that conclusion, I will just show you how it plots in this delta C14, delta C13 plot, where you have these black dots here are the dots are the sediments along the river to shelf continuum. The triangles are the river, the organic matter in the river values, the particulate organic matter values. And what you see is very often seen also in other studies is that the organic matter, which is mineralized, has a delta C14, which is much is enriched compared to the source, and this is linked to the fact that that it's most probably linked to the in-stream production of river, which provides this very labile organic matter that gets mineralized in the sediment. So we made a tentative river plankton kind of circle here, which circles the value that we have found in the literature for the river plankton. So it's very consistent with the fact that that this is probably the river plankton that gets mineralized in these sediments. So if we come up with a sort of simplified source to sink scheme, we have the erosion upstream, which provides refractory organic matter. That's what I plotted here in brown. And in the lower course of the river, where we have the nuclear plants on the Rhone River, then they discharge DIC 14 rich discharge in the sediment, yeah. And this marked the labile OM, which of the in-stream productions. That's what I marked in green here. And when it comes to the delta, then we mentioned that the recycling is based on this more greenish C14 mark labile OM here, which is recycled, and the rest being buried in the sediment, which is more linked to the erosion and refractory organic matter. So this paired isotope help us to assess the sources of organic matter and their fate in the deltas. So now I see that the time is passing very quickly, so I go to the extreme events and their role and influence in the recycling and preservation of organic matter. So the year 2008, quite some time ago, we had the recording of two different flood types. One flood type was in June 2008, and it was an organic pore, thick deposit. Thick, when I say thick, it was in one event, was 30 centimeter of sediment that was deposited. And in the same year, in November, we had a more classic flood, which was organic rich, a lot of organic debris, and a thinner deposit of only 10 centimeters. So I will not go into the details here, but just to show you that it was the first one in June was really organic poor because it was less than 1% of organic carbon, whereas the November one had more 3% or more. Okay, then this June flood had a large effect on benthic mineralization rates, here seen as the oxygen demand of sediments. This is the classical picture on the Rhone Delta. So this is the in red, the large oxygen diffusive oxygen fluxes, in blue, the smaller ones, and we have large oxygen fluxes near the sediment, near the river mouth, declining to offshore. So that's the classical way, and that was the case in April 2007. And after the deposition of these 30 centimeter flood deposit, we had complete weaker degradation of organic matter near the river mouth, and this was really prominent in that part where the values were really comparable to what we see on the shelf. So one might ask why, and we'll see why in the next one. So I will show you this transect of oxygen demand in the sediments. And what we can see here is that in the reference condition, the one I showed, we had larger oxygen demand near the river mouth, declining very quickly in the pro-delta, and then flattening off on the shelf. So when you go further away from the river mouth. But what happened when the deposition of the June flood, we had this lowering of the degradation of organic matter traced by the oxygen consumption. And interestingly, when we went back to after the November flood, which was more organic rich, we found that the values were much larger again, and they come back to somehow the reference conditions. And this was linked to the fact that in the reference condition, we have a lot of organic matter in the sediment, which is both a large quantity and also a large lability of organic carbon. But when we went to the June flood, then the organic carbon was lowered, but less than around 1% in the sediment, and with the low was quite refractory over there. So it was really the mineralization was limited. And then when the November flood came back, it brought again a large quantity of labile organic matter, which triggered again the large consumption of oxygen. So now if we look deeper down in the sediment, so now again, we go to a scale of centimeter, of tens of centimeter scale, from before the flood here to after the flood here. We found that with the 30 centimeter deposition that we had at this time, the organic carbon went down from 2 to 3% in the sediments to 1%, which I showed before, and that the DIC also was lower. That was just 1 week after the flood. So there's a major reorganization of the solutes in the sediment column, and also the sulfate was also pretty flat and pretty near the concentration in the bottom water. That was for the June flood, 1 week after the June flood. So this very poor organic carbon flood. And when we moved to the November flood, which was the second flood where a larger concentration of organic carbon was deposited, we can see that here up to 2.5%, up to 3%. Then we had a rapid regrowth of DIC. You can see that here, but we had also the memory effect of this organic poor sediment that was lower in DIC, and we could also see that this increase of DIC here was linked to the decrease of sulfate reduction. So this large increase of sulfate reduction. So thanks to the work of Stanley Moore, we are able to use a model to calculate the mineralization rate on the fluxes associated to these different flood depositions. And what we were able to calculate for these two floods was that in any case, the deposition of organic matter linked to the flood deposition increased the mineralization rate, the overall mineralization rate. Here you see before the flood, it was up to 200. So if I point here in that red square, and went up to 400, decreasing back to the initial. And you can see also this green color is the sulfate reduction. So it's the sulfate reduction that gets really increased at this time. Whereas after the organic rich and thinner deposit, the mineralization rate went up to a factor of 5, up to above the initial, and then went back also very quickly to after a few months, sorry, to the initial, also carried by the sulfate reduction, because of course the seawater is full of sulfate, so sulfate is used a lot in this for the mineralization of organic matter. Now, if we look at the effect it has on the fluxes, it has a very contrasted effect. The first one produced a decrease in DIC flux, a large decrease in DIC flux that then relaxed over a few months, was the second one that has a very positive flux on the positive effect on the DIC flux, which increased by a factor of 4 to 5 here. When the organic matter, the labile organic matter was deposited, it really increased the DIC flux. And so this is also based on model results, because at this time we didn't made measurements of the fluxes, unfortunately. And we can come up with a sort of a schematic diagram where after the first flood, most of the DIC produced was stored in the pore waters, and with a little efflux out overall. whereas in the second one with the thinner deposit, richer in organic matter, the flux out was much more important and the storage in the pore water was much lower. Okay, then I come to my conclusion, just to show you also on this graph that these rivers, they never stop depositing the organic matter. This is the Sentinel-2 image from yesterday or the day before, the 12th of March, 2024. So floods continued on and continued to feed the ocean. So and I hope I have convinced you that these rheomars are hotspots of recycling and also burial. I didn't talk about it today, but I will probably be a subject in the further webinars. I think the Rhone Delta is a good example because it's a medium-sized river. It's possible to have a synoptic view of the river over a few days. So it's interesting to study all the deposits and also the river plumes. Also showing that these sediments are actively involved in organic matter processing at different degrees. Larger processing near the river mouth because of its point source, and a weaker processing offshore. And that this gives rise to important fluxes of DIC, oxygen, and alkalinity, which I didn't talk about today, but from the sediment to the water for DIC and alkalinity, and from the water to the sediment for the oxygen. That the origin of organic matter stored or mineralized is very often different. So we have the fluvial organic matter from the river, which is mostly reprocessed, while the semi-refractory organic matter from erosion is mostly buried, and it represents most of the organic matter which is deposited in these sediments. Also, one thing that I think is important here is that extreme events are a norm in these environments. So we tend to think of them as singular events or disturbing events, but they are more than disturbing events. They're really a norm. I was on my one of my transparency that 80% of the organic matter in the Rhone Delta is provided or produced by floods. So it's really the norm is events, and we should put efforts to understand the diversity of these floods and because they largely shape these systems, and we've made several attempts to work on that. The last one being the Ferra et al. Paper that was published a month ago, 2024, in Biogeosciences. You can go on and have a look at it to see what work we're doing on that. Just we have this new project that Kanchan mentioned before. So the objective are observing, modeling, and simulating coastal oceans during the 21st century. It will cover all the French coast, from the north of France to the Atlantic coast and the Med coast. It will last for 6 years, so we'll have some time to work on that. And the idea is also to propose solutions to environmental managers. So we'll work with these environmental managers to come up and propose solutions, if we can, for the river input, for example, to the sea. And keep in mind that this will try to couple the influence of anthropogenic pressure and climate change. So there is a website that you can visit, or you can also follow us on Twitter. And with that, I would like to give my acknowledgements to the people that allowed this research to be done. The ships, of course, that we spent almost 20 years on, and the diving team, the technical teams that work with us, and also people that work on the Mesure buoy, which is just out of the Rhone River. Thank you.
Thank you, Christophe. So I would like to open the session for any questions. We have about 8 minutes to take questions. Please feel free to type them in the chat or raise your hand. Yes, I see, Yonggi, you have hands raised. Please go ahead.
Thanks, Liz, for your inspiring work. And you mentioned a very high sedimentation rate in the proximal region of the Rhone Delta. So I was wondering which method do you use to estimate the sedimentation rate? Because it's
Thanks.
high,
Yeah,
30.
that's a very good question because it's a very good question because it's very hard to to get to that. Like if you use lead to 10, like it's a very classical. It doesn't work because then you need for lead to 10 you would need like I don't know maybe 30 meters of sediment to really reach the zero lead to 10. So we use several techniques. One of them used the cesium deposition because there were these reprocessing plants in the Rhone Delta, in the Rhone River. So they delivered a large quantity of cesium, and so this is one thing that we have used. And more recently, we've used because we use a different techniques, which is the differential bathymetry. So we use bathymetric charts from before. And because it pilots like every 1 meter every 3 years. So if you wait 3 years, you can make the difference of bathymetry and calculate that. So that's what we are now doing. And we also, so the interest of doing this bathymetry is that you can not only have one single point sedimentation rate, but you can have accumulation on the, at least when it's sufficient enough to calculate on the whole cone of deposition. So which is also interesting. So it's not only a single point measurement, but a sedimentary deposition that you can have.
Yeah, so for the deposition rate of the floods, I used to read a paper. They use BE7 to trace the flood sediment. They use beryllium 7, to penetrate the penetrated depth.
Yeah, well, you can use that, but barium 7 is too short for estimating the accumulation of sediment because it's only like a 50 days of period. So we've done that, but it's better used for tracing the riverborne sediment on the shelf. That's how we did it. We have a paper by a Chinese postdoc that was with us, Wu, Junwen Wu, and he did that kind of work on that shelf.
Okay, thanks. I will test you more. Yeah, thank you.
Bob, I see you have hands raised. Please go ahead.
Yeah, let me get my video on here just a second so it's not just a box talking to you. Thanks, Christophe. I'm wondering about, and I think there's a question in the chat that I saw along the same lines. I'm wondering about your use of net DIC flux as a measurement of the remineralization, and how are you incorporating the formation of authigenic carbonates and burial of the carbonate side of this system? I know in the Amazon, just to keep going for a second, in the Amazon Delta, about 30% of the carbon that's remineralized gets buried as authigenic carbonates. So significant proportion.
Yeah, we looked at it, and that can be the subject of a further talk on that subject. We've looked at it with Jens Rassmann, who was a student with us, Bruno Lansard and myself. And we ended up, by looking at the calcium power profile, we ended up with a calculation of like maybe 15% of the produced CO2 would be linked to that. But if you go, if you go to this, this is the DIC, so in that region, and you can see that very often of course, it's a very shaky region because there's this piling up of floods that is there. But very often you see what is not the case here. So my example is wrong, but very often you see that there is no real decrease of DIC at depth. So definitely this is the other example. So because even at depth there is so much of organic carbon that is mineralized that it's still the IC continues to increase at depth. And but there is still some you can check that out with the calcium profile. And we have a student, Eva Ferrar now, who is really looking into that more closely. This precipitation of carbonate at depth, yeah. So, but again, one should also be aware that this precipitation of carbonates is also an additional source of CO2. So it's not only a sink for carbon, but it's also a source of CO2. So we're working around these budgets now, trying to see how it goes.
Good. Just a comment about the sediment accumulation in these systems, and I think you're mentioning and you're focusing on episodic events is absolutely critical. But but in looking at that, one of the things I think we have to be aware of is its sedimentary dynamics. That sediment can move from one place to another, and you can erode places and accumulate the sediment in adjacent places, and the net accumulation that you measure, say, by seismic accretion upward, may not be a very sensitive measure of the dynamics that are forming these mixed layers, these mobilized layers. And so I think one of the things we need to do is have much more frequent sampling in these areas in response to physical events, whether they be flood events from the river or storm events on the marine side of these systems. But anyway, I think you made some really good points.
Yeah,
thank you.
You're right, and I agree that this dynamics is very important in both probably the recycling of organic carbon that you've showed very nicely offshore the Amazon with these mobile muds on this reactor, these suboxic reactors, and it's certainly a very important component of these. What I just want to mention here is that we've made observations using altimeters, for example, of the sediment and the storms, the big storms that promote these big waves in this delta. They erode somehow, the very big storms erode 2-3 centimeters, the small storms 1 centimeter. So there is some dynamics, and it's very important in terms of redistributing the sediment offshore in the Pro Delta and offshore. But the main balance of it is definitely towards deposition, and it's maybe 90% of what gets deposited will stay there. So it will compact, accumulate. A part of it will be displaced. I'm meaning just for the very near shore region, 20 meters. But probably 80 to 90% will stay there and not be moved away. So everything that is the internal recycling of it is also very important. But I agree that also the secondary, I would say, dynamics is important for feeding the shelf, feeding the rest of the Pro Delta. Yes.
I think Garrett also had a similar line of question about carbonate minerals. Garrett, do you have anything else to follow up on that question, or you are good?
Yeah, I was just wondering because the Rhone River also. Sorry, yeah. Now you can also see me. Because the Rhone River is one of the few rivers that are actually rich in deltaic carbonate minerals in the sediment.
Mhm.
So I was wondering if that also contributes to your DIC signals, if it dissolves in the sediment or maybe acts as a nucleation substrate for carbonate orthogenesis.
Yeah, well, the carbonate concentration, the solid carbonate concentration, the solid in these sediments is around everywhere more or less the same, 40%. So 40% of the sediment is carbonate. So it's pretty, you're right, it's rich in carbonate. So we have a thesis going on dissolution of carbonate in the very top layer. One thing we're sure of is that deeper in the sediment, at least for the pro-delta part, there's no dissolution because it's very largely oversaturated. So we know that we've made a lot of different measurements, and this is Jens Rassmann thesis. But for the very top layer where the oxic mineralization goes on and the reoxidation of reduced species that produce a lot of acid, a lot of H+, this is still in question. So we're working on that. With a student, Eva Ferreira is working on that, and that's something that will come out shortly. We think that so far the belief is that it's so oversaturated in the water that it will not dissolve, but because the decrease of pH is so strong. It could be a very thin layer that could be dissolved. So we'll have an answer very soon.
Okay, cool. Interested to hear that.
Thanks.
We have one last question on the chat. Can you please elaborate what is organic and inorganic carbon in sediments? I think it's referring to the nature of organic carbon in the sediments, or Damodar, if you're online, can you please elaborate on that?
Okay. Well, the thing is that I refer to the organic carbon in the sediment very often as the trash effect. So what you find, the organic carbon you find, and we find in the sediment, that's what I wanted to emphasize in my talk. What we find, the organic carbon present in the sediment solid phase, is the one mostly that has not been decomposed or mineralized by the bacteria, mostly. And that's what I showed here. I didn't show it very, very nicely here, but we have well, I can go to this one. And on this graph, you might see that what gets mineralized is as this signature in delta C14, and what's in the sediment as this signature. So the remain at that signature, it's mostly older material that gets buried from the erosion. That's what I showed. And the freshy good stuff is mineralized by the bacteria. So it's more like the labile plankton from the river, or the labile parts of the organic matter produced most probably in the river. So there's a big difference between what remains in the sediment and what is the mineralized, and we can see that in the signature, especially the delta C14 signature. But it's not only for this river. Yeah, Bob has already shown for the Fly River in the Papua that it was the same, that the fresh organic matter is mineralized. You can see the signature in the DIC, and the rest more or less is stays in the sediment and is buried.
So I have one question. So you showed the sulfur reduction was really high at the proximal side. So is the supply of reactive iron and manganese low? Because I would imagine that would take off in the proximal side with the deposition of reactive iron supplied by the river.
Yeah, well, the thing with iron and manganese in that zone is very important. I can maybe I'm gonna show you just one result because it's over there. Yeah, in here. you see this red bar. I didn't talk much about it, but the red bar I'm showing here is the sulfide concentration there. So sulfide is almost zero in these sediments. There is very little sulfide, although the sulfide reduction is very strong. I showed that before. So, and this is linked to the fact that there is also a very large and strong iron, probably iron and manganese, but iron cycle in these sediments that captures most of the sulfide produced in FES. We've shown that in a paper that also generates alkalinity fluxes also. We could have another webinar on that at some point. But there's also a very strong iron cycle, and it's probably a one-way cycle because there's so much sulfur reduction at the same time that it doesn't reform and recycle. So that's one thing that we are currently investigating. We have you can find some good arguments with that Martial Teifer on his group worked on in the paper by Rasman in 2020. So then there are good arguments about the iron cycle over there. Yeah.
Thank you. That makes sense. I think that's the end of our talk for today. So we're already past the hour. Thank you so much for giving the talk, and thank you everybody for attending it. I will hope to do this again in a couple of months. Thank you, Christophe.
Thank you again. Bye-bye.
Bye.